Hello, good morning all. Welcome to Krupa's Wireless Wisdom City channel. Through this channel, I address to technical directors, product managers, as well as architects, developers, wireless technical specialists. Hereby I do cover 4G, 5G, and beyond topics. I cover the technical critics, 3GPP specifications, and system design aspects, and most of the core concepts via these channels. Today, we would be covering on the CDL channel modeling, and it would come under layer 1 and 3GPP specification ID 38.900 chapter 7.7, and the keywords would be channel modeling, and under channel modeling we have multiple channel models. Today's will be CDL, that is cluster delay line model channel, and today we would go through the what are the parameters that is governing the CDL channel, such as Azimuth, Zenith, cluster, delay spread, angular spread, LOS, and NLOS. And this is coming under advanced channel modeling concepts in your product design. So coming to the question today, describe CDL channel modeling use cases and the channel governing parameters. Okay. To begin with, in CDL models, the multiple components are grouped into multipath components are grouped into clusters. So as in telecom, we know that every signal is subjected to multipath arrival, and so we call it multipath components. Let's say a transmitter has sent one signal, it has hitting multipaths and reaching to the receiver. So we call it multipath component, and they're grouped into clusters, multiple clusters. If you look at it, it's not cluster, it's cluster. Okay, and each cluster property, each clusters represent a group of multipath signals arriving from the similar directions. Let's say we will come to the point of Azimuth and Zenith in the three-dimensional directions at which it is arriving. So at similar directions for the multipath signals arriving, they are clubbed and is called a cluster. Similarly, each cluster consists of several rays. In other words, you can call several multipath component with similar delays, angle of arrival, and Doppler shifts. Okay, so we see the similar properties and group them and call them a cluster, a single cluster. And in CDL, we'll have multiple clusters to model the channel. And so CDL models support 3D spatial characteristic. We will come to in details where Azimuth and Zenith, how do we cover the horizontal directions as well as the vertical directions, including azimuth and elevation angles, to simulate the behavior of antenna in different directions, which is critical for the system using massive MIMO and beamforming. And let's go through one of the 3GPP quote. CDL models has CDL-A, B, C, and that is mainly catering to NLOS. Okay, your the three channel models, the first three channel models, that is catering to NLOS dominant paths, whereas CDL-D and E are constructed for LOS, that is line of sight. This is non-line of sight, this is line of sight, and the parameter and the detailed tables are being given under 38.900, and these are the tables under which the details has been covered. We'll go through each of them as we cover up the details of the topic. Okay, so as I was saying, these are the tables which 3GPP governing to define CDL-A, B, and your C, and D, and E. Right? So let's look at the what are the parameters that we'll cover. First, we'll define what is cluster. All right, what is normal delay, what is power in dB unit, angle of departure. We'll discuss about that. This is and angle of arrival. Sorry, this is azimuth, angle of departure, and azimuth angle of arrival, zenith angle of departure, and this is zenith angle of arrival. Okay. In a similar way, if you look at A, B, C, they are very much similar, the governing parameters. So these are the governing parameters. And then there is something called per cluster parameter. I have a close eye on this. So this is azimuth spread angle of departure. Okay, azimuth spread angle. Here, remember, I call it azimuth angle of departure. It's azimuth spread. Like you will see that, it's something you can call it like a delay and delay spread, right? It is something related to that. And then azimuth spread of arrival, and zenith spread of departure, zenith spread of arrival, and we'll talk about XPR. Okay. Similarly, coming to CDL-D, you see cluster PAS. We'll come to this point. What is cluster PAS? And there is something called specular LOS path. Okay. And here, if you see, all of them are Laplacian distributions. This is one of the fading distributions that we are covering. I will talk in details. And then normalized delay, power and dB, and as usual we have an angle of arrival, departure, azimuth angle of departure, and arrival, similar zenith angle of departure, zenith angle of arrival. Same way we have also here. And CDL-D and E are also similar, except the governing parameter values are different. Good. So I just noted some of the key governing modeling parameters, which are again covered under 3GPP 39.9007.7, and maybe subchapters you can refer there. Okay, good. So let's get into each of the parameters and understand what are they. Okay, to begin with, azimuth and zenith. This is very critical to know. Understand that azimuth is basically covering my horizontal plane. Okay, so somebody to understand, let's say there is a vertical plane like this. I am how much angle I am from the vertical angle. That is my azimuth angles. Okay, and zenith is something how elevated you are positioned at. Means, let's say this is your horizontal plane, and the zenith is nothing but from the horizontal plane at what angle you are placed. So if you look at the star here, so this is your azimuth angle, and this is your zenith angle. All right. So this is one of the critical concepts. I hope you could imagine. This is like you can consider as an apple you caught in the pieces, and you can see from the apple center as much towards you, that is your azimuth, and whereas azimuth towards the verticals, you can consider like your zenith, or you can otherwise call altitude. Okay, and we call it cluster. Here, if you look at it, there are multi-path components are reaching to the multiple rays. As I was saying, one cluster belongs to multiple paths. So this multiple paths reaching over the mobile system, and they are grouped together. They are called cluster because they are sharing similar delay, similar angle of arrival or angle of departure. So this is one cluster. Similar, this is another cluster. Similarly, this is another cluster. Okay. Then coming to another global coordinate systems, this is defined in your 3GPP. This diagram is taken from figure 7.5.2 from 30.900 3GPP specifications. So if you look at here, as very much similar to the azimuth zenith we discussed. So this is the angle they are talking is your zenith angle. Okay, this is your z-axis. Okay, and this is your y and x. So you can imagine that theta somewhere representing how elevated you are from this xy plane. Okay, if let's say wherever you place, that is your plane, and how elevated it is, that is your zenith angles. And you could see here theta is equal to 0 point to the zenith, right? Theta is equal to 0 point to the zenith point, whereas theta is equal to plus 90, it would come all the way here, right? So that would be your azimuth horizon. It will be your horizons, right? And the zenith and azimuth also is explained similar way from the x-axis, how much angle it is placed here. So if somebody want to know the this is the position to define, so the phi is your azimuth and theta would be your zenith. So this is another way that the GPP has defined very clearly in this figure under 38.900. Okay, I hope you are very clear on this part. This is a three-dimensional imagination. It's very easy. Just if you imagine as a cut apple, it is pretty easy. Okay, don't take it too hard. Okay, now coming to the clusters. As I was talking, in CDLs, we always use, it's called cluster delay line. That's it consists of multiple clusters. So one cluster is having multiple components, and a multi-path components are grouped together and they're called cluster. Each cluster represents a group of multiple components that have similar delays and angular characteristic. When it's angular characteristic, as just now I explained about azimuth and zenith, it defines from which angle the signal has arrived, both in the terms of horizontal plane as well as vertical plane, right? So one cluster, so each cluster, right? Even one cluster will have group of rays or group of multipath components that are having the similar delay and the angular characteristic. That is one of the important points. So this is what we call it cluster, as I was covering. This is the point, the first point we are covering. Okay, then comes normalized delay. Normalized delay represents the relative time delay of each cluster or array with respect to the first arriving path, usually normalized to the maximum delay spread. You can fairly say that it is a ratio, but sorry, it is actually representing the delay of the cluster. Okay, so that is your normalized delay for the cluster path. Then comes to power in dB. Power in dB refers to the power of each cluster, right? Power of each cluster, usually expressed in decibels. It's pretty simple. Again, this power is often relative to the total power or the strongest cluster paths. Okay, generally dB is relative units. Similar to normal delay, this is also power in dB, which is more of relative units. Then coming to AOD, AOA, ZOD, ZOA, angle of departure, angle of arrival, zenith angle of departure, and zenith angle of arrival. If you look at very clear, it is angle of departure. This angle of departure at which the wavefront leaves the transmitter. Remember, this is the transmitter. Angle of arrival. It is arriving at the receiver, right? This is leaving the transmitter. That's why it is called angle of departure. And this is arriving at the receiver. That's why it is called angle of arrival. This is both are azimuth. These two are azimuth in the horizontal plane. The angles that we discussed. And this is zenith. This is again departure. Departure means it departs from the transmitter, and here arrival, it arrives at the receiver. Okay, and this is both are covering the zenith, more of the elevation angles with respect to the horizontal surface. Okay, so this gives the spatial coverage. I mean the angular simulation for the channel. All right. Now coming to the fading distributions, I think all telecom engineers somewhere or other have to have understood that there are channels that can only be defined using some kind of distributions. So here we come to the fading distributions. We'll come in details. Here we have signal amplitude that variations, how the signal amplitude variations, that is something we have to define. So that is defined using kind of Rayleigh, Riccian, and Nakagami. In our case, we'll see that CDL-C, it is using Laplacians. So the distribution profile, the amplitude variations that can be defined for the CDL channels are using Laplacians for the LOS dominant channels. We'll cover for that. And coming to the specular line of sight, Okay, you'd notice this is what it is defined here. They call it a specular line of sights. Okay, this, so we are covering this part. So specular line of sight path refer to the direct, unobstructed path between the transmitter and receiver where the signal reflects off a smooth surface, similar to how light reflects off a mirror. The term specular, see, somewhere you need to be very, need to appreciate. It is called specular line of sight. Line of sight, I think everybody understand. It's a direct transmitted to uh, receiver without any obstructions. It is reaching like a direct line of sight. And the term specular in this context comes from the optics, where specular reflections, right, describe the reflection of light from a smooth surface in a single directions. Generally, when light hit any surface, it scatters. It creates multiple components, but here they call it hits a smooth surface instead of causing diffused reflections which scatter in many directions. It is not that way. So you should be that reflections you should be able to easily define. So it is very specular line of sight arrival. And then coming to the cross polarization ratio, XPR. XPR is the ratio of power of the copolarized component to the cross polarized component of the electromagnetic wave. So the electromagnetic wave that for the channels that is getting transmitted. So this is the ratio of the power of the copolarized component with the cross polarized component. So that is the definition of XPR. And then angle spreads. As I was talking, one CDL cluster component, it's like a covers similar angles, right? So it's a dispersion of angles. So we cover, that means it is a spread of angles. So in a very simple way, like the way you call delay versus delay spread, similarly, a single angle versus angle spreads. Okay, so that is about angular spread. Then we come to the cluster power azimuth spectrum. This is cluster PAS. You would notice here cluster PAS has been defined here. So, so cluster PAS nothing but in a CDL channel modeling refers to the distribution of signal powers across different azimuth angles within a specific cluster of multiple path component. Okay, so basically it's more about, you can call it the distributions, right? The power distribution across the different azimuth angles within a specific cluster for a given cluster of multiple path component provides a detailed representation of how the signal power varies with respect to angle of arrival or the departure for a cluster. Okay, so with that we covered the very much details about all the CDL channel parameter, and we can look at it here now. If you see here that the ABC, they have only they have about, if you look at, take an example of A, they have 23 clusters, and the normalized delay has been defined as here, whereas power in dB and azimuth angle of departure, azimuth angle of arrival, zenith angle of departure, zenith angle of arrival. And you can see here angular spreads of azimuth spreads of departure, azimuth spreads of arrival, similarly zenith and both the zeniths, departure as well as arrival, and XPR, right? Those are the values which we have discussed in detail. They have given. So the ABC, only the value changes, remember, ABC are very much similar table parameters, governing parameters, only the value changes. Whereas D and E, they typically, ABC, remember, they cater to the NLOS dominant channels, whereas D and E cater to the LOS dominant channels. Whereas in LOS, typically they have chosen Laplacians. I will now cover why they chosen the Laplacian distributions. Okay, and we discussed also already cluster PAS and specular LOS path. All right. Okay, so the final concept of for the today, why Laplacian distribution used for LOS channel modeling. Okay, so for that, have a look at the Laplacian distribution, how it look like. Here, there is a comparison. If you look at here, this is the Laplacian distributions. This is your Gaussian distribution. If you see, Laplacian distribution is very spiky in nature, is not it? Whereas Gaussian is pretty smooth, unlike your Laplacians, but it has a very fat tail, right? But if you look at this is the comments about the Laplacian distribution. The peak of the Laplacian distribution sharper than Gaussian, right? It's pretty sharper, whereas the tail of the Laplacian has fatter. If you look at the tail, the blue line is fatter. It's going above the red lines, the tail, right? So that is, and that is why Laplacian distribution also is used for non-Gaussian distributions and for impulsive noise. So we'll go to the true motivations and characterizations of the Laplacian modelings for the CDL channels. Hereby, if you look at in the real world LOS scenarios, the angular spread of the multiple path components tends to cluster around the main LOS directions, right? This is one of the reason. The Laplacian distribution, which is characterized by sharp peak at the mean. This is very, very critical, right? Sharp peak at the mean and heavier tails compared to the Gaussian distribution is well suited. That is the reason it's well suited to model this phenomena. So, as it was explained in real world, I mean, this is what the observation they would have taken from statistics of the data collected from the real world field scenarios. They have observed they have sharp peak at the mean and heavier tails at the at heavier tails compared to Gaussian distribution. That is why they have gone for Laplacian distributions. All right, which is very important. That is why it helps accurately capture concentration of energy around the main path, that is LOS path, and gradual decrease in power as the angle deviates from the main directions. So, okay. So there is also similar lines. So here also explains. So we covered this. So in similar line, empirical measurements in various environments, urban, suburban, and rural, have shown that distribution of arrival and departure angles for MPC often follows a Laplacian shapes. So this is very, very important, particularly in environments with a strong dominant path, that is your LOS path. Okay, there is also another critical path that talk about. So using the Laplacian distribution, LOS modeling align with the observed data, leading to more accurate simulation of propagation characteristic in environments where one strong path dominates, right? And there is a last but not the least, heavy tails for the outlier, right? The Laplacian distribution has heavier tails. We discussed it has heavier tails and a sharp spike at the mean than the Gaussian distribution, which means what? It can better model the presence of significant multipath component that deviate from the main LOS direction, but still carry considerable power. So which is not getting addressed by the Gaussian distributions. So this is very, very critical points. So if some of the multipath component that deviates from the main LOS directions but still carry considerable power, Laplacian is much better suited. So to sum it up, the Laplacian distribution has a sharp peak at the mean and a heavier tail compared to the Gaussian distributions, and that really characterize the real world LOS dominant scenarios, and that is what is being used in CDL-C and CDL-D. Okay, so to sum it up, we have covered in very details about the 3GPP governing which are for dominant channels, and CDL-D and E, which is LOS dominant channels, and very categorically we have discussed also why Laplacian also they have selected for -D and -E. I hope you enjoyed today's sessions. So if any questions or any open points, kindly post it in my channels. Thank you all for spending time for today. I wish that if you had enjoyed, kindly I request to like the channel and subscribe in my channel so that it motivates me to add more details that will help your technical understandings. Thank you very much. Bye bye.